Well, good afternoon, everybody. Welcome to Kistler webinar on hydrodynamics applications. I'm glad that you joined us today to this very interesting webinar. My name is Martin Betschart. I'm product manager for generic piezoelectric force sensors at Kistler. Please be aware that today's webinar is recorded. The recording will be shared with you all and be made available after the webinar. Be aware that you are muted on purpose. If you have any questions during the webinar, please use the Q&A box on the right-hand side of your screen. After the presentation, we'll answer the most interesting questions of the Q&A section, or we get back to you by email if we are not able to answer all the questions on time. Now, I'm proud to introduce you today's presenter, Bill Zwolinski. Some of you already experienced him in action at the last space webinar. Bill holds a master's degree in electrical engineering, specializing in signal processing and controls. Prior joining Kistler some 20 years ago, he has worked in the field of underwater acoustics and has been chief engineer for the Navy carrier landing systems at Textron. Currently, Bill is business development manager for test and measurement applications at Kistler, and at the same time acts as an application engineer. With his extensive know-how in both the mechanical and the electrical world, he's heavily involved in solving our customers' measurements problem. And now, we're all curious to learn something new. Bill, I hand over to you. Stage is yours.
Let's get started. So the agenda today is going to be a bit of an introduction on hydrodynamic applications, as well as a review of piezoelectric principles of operation. We're going to touch upon measuring chains, primarily the charge amp and data acquisition side of the equation, and certainly go in and introduce some force, pressure, and acceleration measurement techniques and application considerations for sure. And then we'll wrap it up with a brief summary, and I'll be looking forward to your questions a little later today. So as far as hydrodynamics, there's quite a bit of opportunities for physical measurements. You have quite a bit of facilities out there, which are tow tank facilities, wave tank, the cavitation tunnels, as well as sloshing platforms and so forth. So there's quite a bit of, I'll say, facilities that people use to make various analysis. Certainly, the applications are looking at reaction forces and moments of structures. It could be models or structures. Seakeeping tests with wave motions and accelerations and so forth. Ditching for emergency landing on water, the effects of that. Ship maneuverability, stability, and also propulsion testing and cavitation evaluations. Certainly with wave impacts, looking at pressure distributions of the wave impacts, as well as it could be even the reaction forces and moments of the structure itself. Certainly, we're going to touch upon the topic of rise time and bandwidth. And this is a concept that really is important to understanding, getting a high fidelity measurement. Having adequate bandwidth for the measurement is rather important. So we'll touch upon that. And then lastly, we'll, the hydrodynamics and vibration of structures, when, water flow, laminar and turbulent flow occur, there's loads and there's vibrations on structures. So certainly there's opportunity there to measure this with accelerometers and force sensors. So here we go. So as far as the piezoelectric instrumentation goes, we're primarily using a quartz piezoelectric material, as you see in the force sensor slide on the first part. You have quartz machined for shear forces or compressive forces, tensile forces. This gets integrated into a sensor and then into a dynamometer. And we'll touch upon what a force dynamometer is a little later. But fundamentally, as you stress this crystal sensor, you get a proportional charge that's proportional to voltage or to force, and that sensor is calibrated obviously for force. and you get a calibration certificate with picocoulomb per Newton or picocoulomb per pound, if you will. With pressure, operates in the same manner. You have a quartz stack, and you're stressing that with a force. You're getting a proportional charge that's proportional to pressure. That's calibrated for pressure events, and then your calibration certificate would be in terms of, say, picocoulombs per psi or picocoulombs per bar, or even millivolts per bar or psi. And then lastly, with acceleration, you also get a proportional stressing of the quartz, and that gives you a charge output that's proportional to acceleration. That's also calibrated in G's typically, or meter per second squared. In terms of piezoelectric and IEPE sensors, I mean, there's some basic top-level understanding. The piezoelectric sensor is one without electronics inside. And this provides a tremendous advantage with an external charge amp. You're able to nearly get infinite rangeability of the measuring chain. Obviously, that relies upon the charge amp characteristics, but quite often you're able to use one sensor to do many tasks, that you're not limited to a certain range. You can actually range it and get the performance benefit of that. Also, with this type of a measuring chain, you get a quasi-static capability. You get the ability to vary the low frequency characteristic of the measuring chain. So you can measure what we call a long time constant, which is a quasi-static, or short time constant, which is more dynamic. And obviously with piezoelectric measuring chains, you can reset and basically tear the measuring chain. So any static mass that you might have is basically removed from the ranging solution, and you can optimize on, say, a dynamic portion or a quasi-static portion of the measurement at that point. So it gives you basically the ability to allocate the dynamic range of the measuring chain to the event that you'd like to measure. Pretty powerful. With IEPE, you have the opposite. You have electronics in the sensor. So what that means is you have a fixed range. So you can't vary that. You have a fixed low frequency. You cannot, adapt low frequency, and you cannot reset the device externally like you could with the piezoelectric. But very, very important to dynamic measurement. IEPE technology is optimized for dynamic measurement only. In terms of the frequency response, it's always important to remind ourselves how piezoelectric sensors work. They're basically lightly damped second-order systems on the high end and single-order high-pass systems on the low end. And what you see here is basically a relatively flat amplitude response with frequency until you get in the vicinity of the resonance. That's quite typical of a lightly damped system. And what happens is, by knowing that, we can actually compute and get closed form expressions for the 5%, 10%, and say 3 dB frequency response or amplitude response as a function of natural frequency. And what you see there is like Fn over 5 is the 5% tolerance, Fn over 3 is a 10% tolerance, and Fn over 2 is approximately the 3 dB tolerance. What that means is that you can choose a wider frequency band by allowing more variability in the amplitude response of the sensor. So sometimes that's important, because as you're trying to make measurements, it might be it's not practical to redesign for a higher natural frequency. It might be that you just want to use the system you have, and you can simply broaden or take a 10% bandwidth, for example, instead of a 5% to accomplish your task. So this topic comes up quite a bit with primarily in force measurement, more so than anything else. But we'll touch upon that a little later. In terms of this piezoelectric technology, I talked about the low end as a single order high pass characteristic. Well, that's what you see here on the left-hand side, a single order high pass characteristic. Basically, you can also calculate closed form expressions for the 5%, 10%, and 3 dB frequencies. And what that means is that's the frequency at which this slope rolls off. A filter, a high pass characteristic, is going to actually attenuate. It's going to have basically AC coupling on the low end, and that's basically what you're doing here. So the 5% frequency you have these closed form expressions, so now you could apply that. So what I've done here is I've taken a typical charge amplifier, which might have a certain time constant settings as a function of measuring range. And the picocoulomb is a measure of charge. It's a unit of charge. And we're focusing mainly here on the piezoelectric solution. So you can see here by applying these expressions, we can see that our low frequency could be on the order of 15, starting at 15 hertz and going up to the highest frequency. Or you could get, say, a 0 hertz or a quasi-static type solution, where you can measure nearly DC or DC events, obviously with the impact of amplifier drift, which is something we'll cover in the next slide. So time constant really defines the low frequency capability of your system. In terms of the quasi-static and dynamic measurement, with dynamic measurement, you're able to measure, transient events and also continuous time events, like you see here. But static events, like the one you see here on the right side with the red X, is really not within its capability because you're really optimized for dynamic measurement. A quasi-static measurement can do all of these. And although with a quasi-static measurement, you set the charge amp up for this long time constant setting, and at that point, the amplifier has a very small leakage current, which appears as a linear drift in your signal, and it might become visible over time depending on what amplitudes you're really measuring. It's fairly common in piezoelectrics, and it's well understood, but I wanted to point that out to you. Certainly, with regard to quasi-static measurements, you have the ability to vary this time constant, and the long time constant setting basically allows you to measure the DC components, the static components, over short periods of time, and the drift can be related to basically 0.03 picocoulombs per second divided by the sensitivity. So you might see a drift of, say, half a Newton a minute for some sensors, or maybe even a quarter Newton a minute, or in pounds, you can see the for those thinking in pounds. So basically, the higher sensitivity sensors, the lower the drift. We're also able to provide a drift compensation solution in areas where you don't have significant thermal transients. You can apply a drift compensation algorithm. But basically, what we're trying to do here is, if you see on the bottom here, you can see a constant force, and you can see a short time constant, and this actually has an exponential decay. So that wouldn't be the proper setting on your amplifier if you wanted to measure a static event. So you would actually set up this long time constant, and that gives you the constant event out. So piezoelectric's a little different from, say, a strain gauge type solution or a DC a measurement technology that's optimized for DC measurement, but certainly very capable and very usable, but it's obviously application dependent. In terms of the piezoelectric measuring chain rangeability, I mentioned earlier that the measuring chain has near infinite rangeability. So say you had one sensor that had a maximum range of, say, 10 kilonewtons. You can actually range this with an external amplifier to a 1 Newton full scale or on up to 10,000. So what that means is that full scale means that the amplifier outputs, say, a plus or minus 10 volt signal. So you would have 1 Newton equals plus or minus 10 volts, or you can use the same sensor to do even higher forces. What you see here is the broadband noise actually scales as a function of range. This is very powerful because you can use one sensor to basically measure large and small signals and actually take a benefit in terms of resolution at the lower ranges. And this is quite, I think, embraced by a lot of different applications, not only hydrodynamics. And I mentioned earlier that you can actually tear the system. If you had a static mass, say, and I give an example here of, say, 100 kilograms or so, you can reset the amplifier just so you're measuring a full scale of, say, 1 Newton around that. So it gives you the ability to optimize or allocate the dynamic range of the amplifier to very low level signal without the burden of taking in the static force or static load of the test article. So quite powerful in terms of getting a high resolution type solution. So now that we've gone through some of the basics, obviously we now need to talk about charge amps and data acquisition. So there is a family of charge amps called lab amp. They're quite unique in the market in that they're high fidelity charge amplifiers, but they're also integrated data acquisition systems on top. So what this enables you to do is get a complete solution and collect your data, either analyze it using one of your analysis tools or perhaps one of the software options that are offered with these units. You can perform your analysis. But some of the key features of these data acquisition systems is 24-bit resolution, upwards of 200 kilosamples per second per channel, all simultaneously sampled. And by having multiple devices collecting digital data, there's also something called precision time protocol synchronization, or IEEE 1588. And what this does is there's an algorithm that operates in the software, quite transparent to you, when you're collecting data, where it aligns the data to a common time base within a accuracy of, say, 1 microsecond or better. And what that does is it provides a common time base for all your data, no matter how many channels you might have. Pretty powerful when you're doing some investigations that require multiple channels of data. In terms of now, taking it one step further, we have a lab amp system which could potentially be optimized for piezoelectric measurement, whether it be quasi-static or dynamic. But what happens if you have different signal types? Well, there's a KeyDAC platform that actually can accommodate many different signal types. Certainly the sensors can be a variety, not only Kistler sensors, but they could be from whatever manufacturer you might be using at your facility. Certainly interfacing to multiple devices with high channel count or different modular flexibility, and certainly software that enables you to now configure the measuring chain, configure the data acquisition, collect data, and then eventually perform the analysis. So this is really the next step to getting a complete solution. Having a multi-purpose modular and scalable data acquisition system that can accommodate many different measure ends gives now the power of accommodating a variety of different needs in a test. It could be that you want to measure temperature, and you can get thermocouples brought in. You might want to measure strain. You might want to measure currents and voltages, and so forth. All this can be integrated on a platform. It's a modular system with various cards of different capabilities, and this is just a snapshot of what you might see. Is that you see many of these modular cards that fit into the rack chassis have multiple functions. They're not just doing one function. They might be doing several different functions. So you get a lot of capability within one module. Each module has its own data acquisition capability on board. So obviously you're getting the ability of a distributed processing network where you get the digital data is all time synced, as I mentioned before, and all put into one data file with a common timestamp, synchronous timestamp within 1 microsecond. So very powerful for devices with multiple means of getting digital data. In terms of software, a lot of times people are faced with, well, how do you coordinate such measurements? Well, the Key Studio Lab is absolutely optimized for setting up projects, setting up tests, and being able to coordinate data acquisition and getting the data into a file that can be then transported to an analysis package, either one you might have at your facility or perhaps a package called JBeam, which is an interactive analysis tool, very easy to use, gives you a variety of plots, and the power of this tool is really in the ability to create reports and generate results in a defined format. So So this is a snapshot anyway of a more elaborate system that could complement a hydrodynamic solution. Obviously, when you get into these packages with modular capabilities, there's a lot of features and benefits of such a system. I just highlight here a few. Obviously, with a professional package, you can interface up to 3 rack chassis. Each module of that chassis, there's 13 per chassis, could perform many channels, 8 to 10 or 12 channels of signal conditioning, for example. So you've got a very high channel count capability, and certainly the software in the back performs all the plotting and FFT work and filters and signal processing to realize a solution. Again, so as a snapshot, what we've done is we've looked through piezoelectric technology. We've looked at force, pressure, and acceleration. We've tried to identify, what the benefits, what the pros and cons might be, and certainly looking at how you convert or how you use the voltages generated from these signals and charge amps or sensors and charge amps to realize a analysis and collect data and actually perform an analysis to accomplish your given task. So now what do? We want to go into force measurement, and we're going to spend a few minutes on this. So I talked previously about a force dynamometer, and what I want to say first is that a given sensor that you might see, a force sensor, is very much optimized for measuring axial loads, okay? So axial loads would be anything, say, going through the center of the sensor, for example. In a lot of hydrodynamics applications, you're not faced with such axial forces. It could be a model of significant size. It could be a structure of significant size. And now it's not so easy to identify, say, an axial force. So what's done is you comprise what's called a force dynamometer, which is basically 2 parallel plates with sensors mounted in between, which basically accomplish the task of taking complex forces and distributing those loads over these 4 sensors or more sensors to then realize a solution and being able to calculate both forces and moments of that test article. With any of these types of applications, analog bandwidth considerations are absolutely critical. You need to always keep that in mind. And the charge amp system that I've talked about usually gives you the broadest band of frequencies that under consideration. The test article a lot of times requires a subset of what the charge amp can actually do. But the real challenge and the real objective of creating a force measurement is really getting the force sensors and fixtures, whether you're using a dynamometer or other fixtures, to realize those frequency requirements of the test article. So it's very much, it could be an iterative process, but certainly it's one that really requires a bit of a discussion with your favorite application engineer and working some models and assessing overall integrity of the system for the requirements. What I show here is several considerations in terms of force measurement, and we're going to touch upon a few of those a little later. But I wanted to give you a list anyways to keep it in mind that when you're approaching a force solution, there's many considerations, some more important than others, but all relevant to making a precise measurement. What I show here is just a table of parameters with typical 3-component force sensors. And there's a force sensor, and there's also what we call a force link. A force link is already preloaded at the factory, and what that means, it's already got a calibration certificate, and with these top and bottom flanges and the preload bolt, it's a self-contained modular piece, a building block, if you will, that you can apply to various measurement applications. Whereas in the force sensor realm, you're also in a modular way, but now you have the ability, when you mount force sensors, you're actually getting the lowest profile possible. Whereas with force links, there is a definite more height in this solution, and sometimes that's a that's not too amenable to a given application. So a lot of times customers will look at, do I go with the force sensor or force link? But I also show you a little bit about the terminology, sensitivities, linearities, crosstalks, stiffnesses are all critical to assessing, how your platform, how your force measurement platform performs. Obviously, all the stiffnesses are great when you want to do an FEA analysis, try to see how this fixture that you're building was going to accommodate whatever test you're trying to make. Inherent to piezoelectrics is very low crosstalk, and I show what the data sheet values might be, but actually the calibration sheet values are even much lower. So it's an inherent benefit of this technology to have very low crosstalk and very high linearity. So basically what a 6-component measurement looks like is you have a device called a dynamometer comprised of, say, 4 3-component load cells. And internal, we will do some internal charge summing to generate, instead of 12 signals, we would have 8 signals. Well, by having this and knowing the geometry, you see a parameter called A, which is the vertical separation of the sensor to the center line. And you see the horizontal separation B right here. And by knowing that, you can easily compute a closed form expression for forces and moments. Now, what that means is you can take these outputs of the dynamometer and directly compute the forces and moments in software, or you can use a charge amp, which actually has an integral summing calculator that can output 6 analog voltages that basically implement these equations in analog circuitry. So there's a couple different ways of going about it. Now, getting back to some of the things I talked about earlier in terms of considerations, I talked about how a dynamometer has load-bearing surfaces. Well, there's certain parallelism and flatness requirements that we like to flow down to doing this. And certainly, there's when you approach a dynamometer solution, you can either do it yourself, you can get something off the shelf, or you can maybe even get a custom one made for a specific application. There's several different ways of going about it. So here you see the load-bearing surface requirements. Whenever you have a force sensor, anything, or a single component or even multi-component, you must preload it to get the highest or the best linearity. But with 3-component sensors, preloading also achieves the tensile and compressive force measurement, as well as the shear force handling. The reason for that is shear force handling is basically given by the frictional coefficient of the sensor, which in this case is 0.2, times the preload force. So you can basically set up your measuring chain to give you the compressive and tensile force handling, as well as high linearity and the ability to transmit shear forces very accurately with the proper preload. I talked about linearity before. The linearity for piezoelectrics is actually quite good under preload. And what I show here is an example where we preloaded a sensor at 450 kilonewtons, and it's like a 0.5%. But if you go to a partial range calibration, you can actually achieve even a tighter tolerance on linearity. So a lot of times when you're using, say, piezoelectric solutions, you have the ability to now range it almost infinitely, like I said. But also what you might want to do is actually be able to get a few different calibration points and be able to then use that as a common platform for a variety of different tests. So now you can dial in a certain sensitivity for a given force range, and you get the benefit of the higher linearity, the better linearity as well, as illustrated here. Preloading also creates a shunt force, and that in effect takes up some force. So your actual sensitivity of a preloaded force sensor is about 6 to 8% or 6 to 9% lower than say what it would be ideally, because the preload bolt is actually mechanically in parallel with the force sensor, and it has not as high a stiffness. It has a lower stiffness than the force sensor, so hence you're going to basically take up some of the load with the preload bolt. Very common, but it's calibratable and fixed. I talked about tensile and compressive force. By preloading to, say, 2/3 of the measuring range of a sensor, you're able to get plus or minus 1/3 this compressive and tensile force handling capability of that sensor. Fairly straightforward, but real powerful when you're doing vibratory type analysis. I also refer to alignments. I mean, sensor alignments are rather critical. Putting together sensors and making sure they're aligned really gives you the best crosstalk. I show an example here where 1% misalignment in X and Y would give you, say, a 2% crosstalk. So quite important. Now, these sensors look round, but they're actually, if you take a close look, they actually have flats on these sides, right? So the flats are actually used to do the alignment of the sensors. And although they look round, they actually have flats on them, which are a very helpful tool. And then lastly, crosstalk. I show here a sensor that's actually got a data sheet crosstalk. But if you go look at what the calibration cert says, you're within, say, 0 to about 0.6% crosstalk in reality. So it's not uncommon. Kistler is quite conservative in their specs, but the proof is in the calibration cert when you see the crosstalks. And in many cases, there's no need to do any compensation matrix for crosstalk for piezoelectrics because they're so inherently low in crosstalk. Unlike, say, strain gauge technology, there might be compensation for high crosstalk, these compensation matrices. So a little less bookkeeping, a little less work involved when you get to the solution of crosstalk. So I want to just show you a brief example here. And in this example here, you have a tow tank, you have a carriage. Underneath the carriage, you have the dynamometer. In this case, the user used force links and built up a dynamometer, top and bottom plate. And he has a model underneath it that he's going to measure the reaction forces and moments. In this case, instead of using 8 channels, the user used 12. He wanted to sample every channel. Obviously, there is no real need to do that. You can actually use only 8 channels and use the pre-summing technique I talked about earlier. This is just a little more information on the sensors and cables themselves, but I've already gone over that a bit, so I'll just leave it for your reference a little later on. But there was definitely some using those selection criteria I talked about earlier was certainly in the discussion. And this is just another example of what you see here, and this is at the University of Michigan. A tow tank application where the engineers over there took a force link. This is one of the smaller ones, and actually built a top and bottom plate and actually wedged these force links in between. And then you see the 4 screw holes, top and bottom, that are mating to these screw holes. And then there's an apparatus here that attaches to the carriage itself. And then you can see here where the engineers are actually instrumenting the boat model with the dynamometer. And you can see here a better picture of that dynamometer in the large boat. It's fairly large boat. But what you see here is really this is the carriage of the tow tank, and you can see there's a void area here on either in the middle where you see water on the bottom. So this model just drops into the water. Here's your data acquisition and capability right here to collect the data straight away. Pretty straightforward, pretty common application. So now what? So now that we have all this background, so what do we want to say about sensors and working underwater? Okay, so there's 2 basic scenarios with measuring force, submersible force. One scenario is the one I just showed, where you have a carriage, and above the carriage are data acquisition computers, and it's all readily accessible. So what happens is you might have sensors under the water, but you're routing cables, IP68 cables, up to the equipment on the carriage, okay? So they're in a very dry environment, and you basically get the benefit there of having charge signals coming up to the charge amplifiers and having this infinite rangeability, if you will, with this type of solution. So when you have this solution, you have a lot of flexibility in terms of the signal conditioning solution. Now, there are other scenarios, which I'll get into shortly, where you don't have a carriage on top, and you have basically a self-contained vehicle with a watertight compartment, which houses, say, power supplies and data acquisition, and you need a fully, a sensor with voltage output that interfaces directly to an underwater vehicle with a compartment that collects all the data. So that's a different solution, but a little less flexibility because you don't have this infinite ranging capability, but still very usable in terms of what is available in terms of sensor technology. What I want to say, here also, you can see these cables are 1698 style cables. They've been qualified for up to 13 bar pressures. Now, obviously, it could be an in-depth. It could be that you're actually at depth at 13 bar, or it could be that you're in a closed vessel like a cavitation tunnel, that you have a certain resonant pressure in that. So whether it's by water depth or whether it's by a pressurized vessel, these cables are watertight for sure. And what you see here is also, the force sensors can be individual. They can be mounted into a dynamometer configuration, and you can also use a dynamometer, off-the-shelf dynamometer, which isn't as highly rated to 13 bar, but it certainly can survive, say, 5 meters of depth in terms of water depth. The cables, again, they're either armored PFA or a TPC type cable, which is more flexible. They have a lot of lengths up to, say 20 meters, 10 to 20 meters. And what you do here is outside the water. This is not a waterproof connection, and you would definitely mate this side to the breakout cable with 3 BNCs, much like what I showed here. Okay, you're basically breaking out to 3 BNCs going to the charge amp, and this is all outside the water. Now here's a case where I talked about where the whole vehicle is submerged, okay, and you have a watertight compartment and you need sensors that operate in a voltage mode, okay. Well, what's really important for hydrodynamics is really to measure this quasi-static loads and moments, and in that you need a force sensor that has basically this long time constant setting. So one that's been used for quite some time is this 9602, and it's basically got an integrated charge amplifier inside, 2 ranges, and the ability to switch between range 1 and range 2. It might be that you want to do some higher range hydrostatic type load testing and then lower range dynamic testing on range 2. What we've done is we've actually optimized and customized certain solutions as well, where the limitation of this product is that it's basically one range, okay? But imagine being able to take all the various sensors that might be available that I showed you on those 2 slides and being able to interface an amplifier that's IP68 to any one of those sensors and be able to use that into a hydrodynamic solution. So now you have almost, endless type scenarios that you can mate sensors together with these inline charge amplifiers, which are submersible to 10 bar, and very much usable, giving you a voltage output and giving you the ability to go long or short time constant with 2 ranges as well. Then another custom solution is a dynamometer that's actually optimized for prop shaft studies. And here you would have a rotating dynamometer where you would have voltage output. You would have the ability to change ranges, much like you see here. And obviously the end user would route the cables along the prop shaft and eventually bring those to slip rings into a data acquisition system. So many ways to use force solutions. So you can go where the charge amplifier is out of the water, or you can go with the charge amplifiers in the water and be able to accommodate a multitude of scenarios. Test scenarios are achievable. One other one I'd like to mention is this is a 6-component sensor, and basically what people like about this sensor is that it's not so big. It's around 90 millimeters by 60 millimeters, so roughly 4 inches by 2 inches. And what you get there is the ability to put this behind, say, geometric structures in flow, and you can measure directly forces and moments without any calculation. And again, this amplifier is compatible. This amplifier here in line is compatible with this sensor as well. So now you get the ability to get voltage output, or you can use it as a if you have a scenario where the charge amp is out in the dry area, you can also use that. So either way, very capable 6-component measurement. Another one I want to mention is a kit that we provide that some customers use to save money and to find more economical solutions. Obviously, when you make your own dyno, you have the ability to achieve what you need, and certainly at a price that's basically your value added. So this kit anyway is really unique in terms of what it provides, and it enables you to then make up to, say, a 900 by 900 millimeter force plate if you so chose. Actually, I think not 900 by 900, but 900 by, say, 300 force plate. What I want to show is a certain example here where you see a structure in flow, and this application, the requirements we got were basically we had 10 kilonewtons in X, Y, and Z, okay, or 20 kilonewtons, I'm sorry, in X, Y, and Z in terms of desired force ranges. You had about a 1,000 kilogram mass, and you wanted to measure forces in moments. Well, by using this kit, you were able to achieve an economical solution and be able to do something like this. With this high of mass, you're still seeing dozens of hertz in natural frequency. So not just static measurement, but some dynamic as well. And then lastly, with anything dynamometer related, you're looking at spring mass systems. So spring mass systems are going to be affected by mass. And with added mass, you're going to get a reduction of natural frequency. And that's really consistent with physics, actually. You're not going to avoid that. And then importance of mounting is really critical to get the best frequency response. So we always will give you guidance on, the more fasteners, the better. Basically mount the dynamometer in a rigid manner. And lastly, with calibration, in situ calibration at the facility can be done using static forces or weights. And at the factory, we use electric actuators with reference sensors and so forth. So many ways to accomplish an in situ calibration, and also what we do at the factory as well. So you get a calibration certificate that has all the parameters of interest. And I just want to mention briefly an alternate technology, and unfortunately this thing is not moving up. No, okay. Yeah, I don't know what happened there. Okay, so anyway, okay, there we go. Let's see if I can minimize this. There we go. There we go. Sorry about that. So bonded foil strain gauge, okay, commonly used in hydrodynamics. Absolutely, force sensors with bonded foil strain gauges. And basically the concept here, instead of rigidity, it's actually flexibility. These bonded foil strain gauges are bonded to metal, which flexes, and there's a resistance change in this bridge. That resistance change is proportional to force, and everything's calibrated in that manner. So you get a proportional force to a certain deflection in the metal. And very commonly used, and I'm often asked, well, Bill, can you make a comparison? Well, it's often hard to make comparisons between strain gauge and piezoelectric, but I took a shot here. It's always application dependent, so you always feel a little bit, well, are there other things you can consider? But fundamentally, where strain gauge comes in is really on the long-term measurements for static force. It's got very good temperature compensation capability, good accuracy for sure. So there's definitely some benefits to using strain gauge. I've already gone through a bit of what piezoelectric offers, certainly the rangeability, quasi-static capability, being able to tear the force to optimize your dynamic range on a measurement, all very powerful. Some people give me feedback anyway on using piezoelectric and strain gauge. I just wanted to leave you with a couple thoughts. The natural frequency of piezoelectrics, users actually like, because it provides a higher frequency capability than what a strain gauge force sensor would achieve. And a lot of times this is due to the high rigidity of the piezoelectric solution compared to a strain gauge. The response time, like I mentioned, the dynamic or the ability to have wider bandwidths, faster response time. And one of the key advantages would be test stand adaptivity, where you can use one test stand, range it for what you need, and be able to use it in a modular manner and configure it in an easy way to accomplish a multitude of measurement tasks. I'm not going to go through the checklist here, but I leave it for you to look at. I've mentioned a lot of these terms, but I wanted to summarize it one last time. In terms of piezoelectric pressure, we've got the same type of scenario here where you've got charge signals, piezoelectric and IEPE, and all the rules sort of stay the same. You get the quasi-static measurement, you get, with piezoelectric, you get the ability to range the measuring chain, vary the low frequency characteristics, and so forth. IEPE is relegated to dynamic measurement only, but very, very much used at times in hydrodynamic solutions. So, making the proper choice often requires just a bit of a talk with your favorite application engineer, and you can dial in the right solution. We also have piezo-resistive measurement solutions. Now, instead of piezo-resistive solutions operate in a flexure design, where you actually change the resistance of this bridge, and that resistance change is proportional then to pressure, and it's all calibrated in a very precise manner. So Kistler tends to use a cavity-etched micromachined silicon element. So if you're really looking for DC pressure, static pressure for long periods, doing absolute pressure, gauge pressure, differential pressure, this technology is really what's often used. Certainly some of the benefits of this piezo-resistive technology is high gauge factor, meaning you need less deflection in the metal, surrounding metal, to get a higher output, and very high burst pressures. So you get, if you have a bad day of testing, you don't have to buy new sensors as readily. So that's a real plus. Certainly, the other advantage is 2 kilohertz of bandwidth, and certainly rise times are on the order of, say, a couple tenths of a millisecond for this technology. I talked already on the dynamic pressure capabilities of piezoelectric. Pressure pulsations, quasi-static pressure also are very much achievable with piezoelectric and IEPE piezoelectric technology. For piezo-resistive technology, you need low bandwidth dynamic pressure measurements, low bandwidth pressure pulsations, and certainly static pressure is absolutely where it's optimized. And here's a checklist again. Some of the parameters I've talked about before, but linearity is always a key, error source frequency range. These are all quite important selection parameters to consider. I just wanted to briefly introduce a couple illustrations here where, I mentioned this long time constant effect, and what you see here is a long time constant signal where you have a nearly constant signal over a long time. But you see here on the signal, there's a bit of a ripple. But if you basically just set the charge amp up to a short time constant, you basically AC couple this signal, so you no longer have this offset, and you now can actually get high fidelity visibility on this this AC component that's riding on the signal. So, piezoelectric offers some really interesting techniques to optimize a solution on whether you want a total solution with total pressure or optimize on the dynamic variations. Obviously, with transient or quasi-static or transient quasi-static events, you need a time constant that's always on the order of 100 times the event duration. And what we show here is just if you do this, you don't end up with, say, disparities in the measured, signal versus the process signal out of the charge amp. So again, a general rule is time constant is 100 times the event duration. This is for short duration transient event, transient quasi-static events or static events. You also mentioned rise time for piezoelectric. Very much a higher, much shorter rise time. Rise time is a function of the natural frequency, as you can see here. But and natural frequency is a function of rise time. But basically, The higher the natural frequency, the shorter the rise time of a system. And rise time means response time. I show here also with natural frequency and in terms of response time. You see here a pressure sensor that has, say, 100 kilohertz of bandwidth, and you have an 80 microsecond pulse. You see that it can measure that quite accurately. But if you have a much lower bandwidth sensor, you struggle to measure these very short duration events. So bandwidth is very important to pressure measurement, not only for accurately resolving the signal, but also response time, very important. Submersible pressure sensors. Nowadays, there's Viton cables that are welded to piezoelectric sensors that provide watertight capability to 16 bar. That's 232 psi. And this is basically a close-up picture of it, what you see here on the bottom. Now, just looking at the sensor is actually, with piezoelectrics, they're actually optimized for very small diaphragm. So here you might have a 5 millimeter diaphragm or 2/10 of an inch. The rise time is based upon a natural frequency here of, say, 215 kilohertz. So you have a rise time of 1.4 microseconds. I showed you with piezo resistive, it's like 2/10 of a millisecond. So big difference, okay? So when rise time is really critical, a lot of times piezoelectric sensors are critical as well, or are often used. What I want to also say is sensors like this, the 601C, has actually been optimized for low thermal shock sensitivity. The reason why I mention that is that, in these applications where you have wave impact, where you might have air on the sensor and then air and water, you wouldn't think that there's a big temperature disparity, but there's enough temperature disparity that if you have a sensor that's not got a very good thermal shock sensitivity, you can see a very much a remnant, an attribute of thermal shock in your sensor. And this could be on the same order of magnitude of the pressure you're trying to measure. So having a low thermal shock sensitivity sensor like the 601C really complements a slamming, sloshing type measurements where you have air and water, variation of temperature. The 603C basically is the same type of construction in terms of diaphragm size, but also fast rise times, even faster because it's nearly 500 kilohertz of bandwidth. So this is used for much higher pressures, up to, say, 15,000 psi or 1,000 bar. Here's an example of a wave impact or slamming application where you see basically these small pressure sensors, small diaphragm. You can mount those very tightly spaced. So there's a very good spatial resolution when you use piezoelectric sensors because you have 2/10 of an inch diaphragm, 5 millimeter diaphragm. What I like to say when you're doing these types of walls, it's always important to use a very sturdy plate, a steel plate. I've seen where plexiglass is sometimes used, and plexiglass actually has a very low Young's modulus compared to steel and aluminum, and you get actually bending, and that could actually create errors in your measurement depending on the sensor you use. So I often recommend taking a metal plate, installing your sensors on a metal plate. Even if you have a plexiglass tank, you can accommodate a watertight solution with mounting this plate to your plexiglass, and it gives you a very stable platform to measure pressure. I also measure, this is direct mounted sensors, but there's also options for adapters, which you can basically use instead of a direct mount, but usually you need more room or more separation between sensors to use one of these adapters that you see here. And certainly this is an example of a very fast transient wave. When you do wave impact or slamming, you see something that looks like this curve, time versus amplitude. You also have cavitation water tunnel testing, and in this case you might have a pressurized vessel that I mentioned before and some object under test. You have some dynamometer or maybe rope spinning that propeller shaft, for example, and you might want to evaluate cavitation, okay, with regard to pressure sensors being mounted in the vicinity of this propeller as it is operating. Very common technique to look at cavitation, but also with cavitation tunnels, you're also looking at forces and moments. We work with some facilities that instrument dynamometers in this regard, we also look at noise and vibration measurements in the same context. So it's not only just a pressure measurement, but a multitude of measurements going on in a cavitation tunnel. Sloshing is for liquid natural gas, LNG tankers, which these tanks have to stand up to very high loads, in very high sea states. So there's a lot of work going on to ensure that there's no accidents at sea for sure. So what's typically done is you have a model like this, where you have a hexapod, where you have a plexiglass model, and you have a metal plate filled with these sensors that I talked about. This plate is adapted to the model, and then you go through some various motions to assess the wave impact on each sensor. Because the sensors are only 0.2 of an inch OD or 5 millimeter OD, you're able to get a very high spatial resolution in terms of this measurement. And with the piezoelectric solution, you have a very high response or very fast rise time, so you can achieve these very high fidelity curves that you see down here with this motion hitting the pressure sensor. Lastly, because the pressure sensor has a well-behaved thermal shock profile, you're able to get true measurement of the pressure impact of the wave, and not having so much in terms of the thermal shock of the event, which is very undesirable and very hard to get rid of. And having the sensor that has that inherently, very key to a good measurement. So I'll go into acceleration. I got a few minutes here. There's a lot of different terminology for acceleration, vibration, shock. They're all measured with accelerometers. I mean, acceleration could be that you're in a race car around a track, that you're measuring static and dynamic acceleration. Vibration is purely dynamic, okay? You could have a gear train, and you're measuring the vibration of that gear train. Shock is basically a transient event, short duration transient event. All of these events are measured with an accelerometer. Again, with this technology, you have piezoelectric and IEPE. All the rules stay the same. You have a charge amplifier that you can range it externally for a piezoelectric. You have a IEP accelerometer. It's optimized for dynamic measurement. And then a lot of times IEPE accelerometers are often used in hydrodynamic applications. There's also MEMS capacitive accelerometers. MEMS stands for micro electromechanical system. What this sensor technology is it's actually a DC coupled technology instead of an AC coupled, meaning that you can measure static acceleration, you can measure local gravity. And that's basically given by a spring mass system suspended by a cantilever beam, encompassed by two top and bottom electrode. As this moves under acceleration, you get a change of capacitance between the spring mass and the top and bottom electrode. That change of capacitance is directly proportional to acceleration. And then, the unit is calibrated for that, and you're getting millivolts per G out of such a sensor. So these are often used for large structures. Say you're doing structural analysis with large structures, very low operational modes. These are perfect. You get 0 hertz on up to, say, a couple kilohertz of operation. The frequency response, again, DC response for the MEMS capacitive, and AC coupled response for the piezoelectric. And there's also various reasons why you choose one over the other. But fundamentally, what I look at in technology is really, what is the frequency? Do you really need low frequency? And if you do, the MEMS capacitive is really one of the ones people choose. If you need high dynamic frequencies, well, then the piezoelectric is often selected. Then in terms of solutions, I mean, you have integral cable, IP68, triaxial IEPE accelerometers, qualified to 10 bar for 48 hours. You get G ranges from 50 G and up to 2000 G capability. You get single axis versions of that, capable to the same 50 to, say, 2000 G range. And by the way, all these are tested to 10 bar for 48 hours. So very, very much watertight from the factory. Then also the 8396, which is the MEMS capacitive accelerometer, triaxial accelerometer, also is a integral cable solution, IP68, also qualified to 10 bars. So with regard to vibration, underwater vibration, you can accomplish it with a piezoelectric IEPE, triax, single ax, or even a triaxial MEMS capacitive accelerometer, depending on the requirements. Then I have a checklist here of some of the selection considerations. I've gone over quite a bit of these on other measurands, but when you're settling in on what sensor to use, these are often topics to discuss with your favorite application engineer to make sure that you're having the best solution for your measurement. And that's just a summary slide of all the accelerometer, watertight IP68 accelerometers that we talked about. What I wanted to say is that each sensor is tested under pressure on the at the end of the production line. So it's not something that's just put together and you hope that it works. It's actually tested and verified that it works for those rated pressures. One last thing, and this is a rough as a quick summary. We've reviewed a lot of different applications here, certainly tow tanks, wave basin, slamming, sloshing, propulsion tests, propeller tests. We've touched upon accelerometers, which can measure the flow-induced vibration, structure-borne vibration, as well as doing structural dynamics. So a lot of times the watertight IP68 solution is required in some of these applications. Sometimes just a conventional sensor or signal conditioning is required. But what's interesting to know is that there's quite a few choices, and certainly what you see here in the presentation is really a product range that's optimized for the application. It really understands the difficulty of making measurements in the hydrodynamic applications and providing watertight solutions over many measurands and many technologies to accomplish that. On that point, I'd like to, wrap up by saying thank you all for joining. And at this point, I'd like to go back to Martin, and maybe there are some questions I can answer for you folks.
Yeah, thanks a lot, Bill. That was a lot of information in a quite short time. We have some questions. We have 3 questions that were handed in during this session. I will ask you quite after this, but just for those who wants to pose a question later on, drop us an email and so on, and we're gonna be back to you with the answer and answer you the questions later on. But to the first question that was posed was regarding drift. Can you quantify the drift in newtons or bar, just to get a feeling for it?
Yeah, the drift in newtons is roughly a half a newton per minute. This would be a maximum you would expect. Okay, and this is for a sensor that is say nominal sensitivity. Drift again is there when you have a long time constant quasi-static operation. But what happens is drift is a function of sensor sensitivity. So there's some sensors that have higher sensitivity than others. So the one I mentioned, the 4 picocoulomb per newton, gives you about a half a newton per minute, and that's your nominal sensitivity. You're rarely less than that, and usually more than that in other sensors. So that would give you an idea from a force perspective of what the drift might be.
Okay, thanks a lot. Then a second question was, do you have any piezo-resistive solutions for force measurements?
It's a good question. We have a very limited range of solutions of strain gauge based force measurement. So it's not as comprehensive, but we do not offer anything that is watertight at the moment. So it's certainly something down the road to consider. But yes, good question, but not quite yet a solution from a watertight perspective and a limited range and single component strain gauge measurement.
Okay, thank you. And the last questions from the session is about pressure sensors. Why is a flush mount to be preferred compared to direct mount?
Okay, so the terminology is a little, I maybe didn't explain it too well. I apologize for that. Direct mount means that you take the sensor and you don't have an adapter around it. You actually mount it directly into a bore. Okay, and this gives you basically, as I showed, 5 millimeter OD or 2/10 of an inch OD, a diaphragm. So you're able to pack these sensors quite tight by going to a direct measurement. The flush mount is different. Is you can mount a sensor flush mount, or you can recess it, or even mount it in a passage. Why flush is preferred is that usually you're measuring wave impacts, and this gives you a good surface area of the sensor to measure the impact itself, and it gives you basically no dead volume, and it's just right out there, flush with the wave impact. So it's quite optimal in that regard. If you go to, instead of a direct measurement, you go to a adapter measurement. What this means is that you take the pressure sensor, this small pressure sensor I showed you, and you screw it into an adapter, and you take that adapter and screw that adapter into your plate. So it's a different way of going about it. Sometimes people think it's a little bit more convenient to have an adapter approach. But again, it's dictated by the application. The tighter the spatial resolution you need, the more impact, the more reason that you want to go to a direct mount. And in sloshing and in wave impact, you really want to see a flush mount solution. And the sensor I showed you, the 601C, is flush mountable. It also gives you the high response time, the very short response time, and it gives you the good thermal transient characteristics of the diaphragm, as well as the small size and tight spatial resolution. So I hope I clarified that a little bit better for you. Sorry about that. I didn't bring that out during the discussion.
Oh, well, you did now. Thanks a lot. And there's a last question just came in from Craig. Any discussion at Kistler about omnidirectional pressure transducers?
Yes, there's not something and if it's the Craig I know, he might be thinking in terms of the blast. So we're going to probably go offline for that one, but no, nothing that I can offer at this time in terms of an omnidirectional pressure sensor for say underwater blast application, if that's what Craig is referring to.
Okay, thanks a lot, Bill. That's it with questions as far as I can see. So thanks everybody for joining and listening. If you still got any questions, just drop us an email, or if you want to have contact or whatever, just reach out. We are here for you. And yeah, thanks a lot, Bill, for the presentation and all the answers to the questions. And hope you enjoy the rest of your evening or afternoon or wherever you are right now, and join our webinar. Thanks a lot. See you soon, guys, for the next one.
Thank you, Martin. Thank you.
Bye. Thank you.